do keep in mind, you don't have to reinvent the wheel to do Yule-Walker estimation. It has been around for a long time. But if you don't understand the basic Yule-Walker estimation, you wouldn't be able to go and predict something new. Times are changing. We have large data sets these days, and one of the machine learning algorithms that is used in time series, two of them. One is LTSM, the other is recurrent neural networks. Well, if you don't understand this, there is no way you're going to understand that. And from a business standpoint, how valuable is prediction? Super, right? It's super valuable. Because if you don't predict things properly, then it is going to affect, for instance, your shares, share price, etc. So in our example that we did earlier, I said I observed a series from AR2, and this observed series resulted in, I'll put it as R here, estimate of row 1.64, estimate of row 2, was it negative 1.64? Okay. We used a calculator and we came up with estimates. I'll show you how you can do it using R. It's pretty straightforward. First, you've got to create a matrix, just like we did it using the calculator. So, the row hat matrix, you can use underscore. I tend to use dots only with R. Row hat is a matrix, and the values were 0.64 and minus 0.16. Number of rows 2, number of columns 1. With R, you've got to specify if it is by row or by column. So if you don't specify, it's going to start filling the values from left to right. If you want it from top to bottom, you've got to specify by row. It's true. P2 matrix 1.64, 0.641. I'll demonstrate with and without by row, n row, number of rows 2, number of columns 2. Let's say I don't specify by row. It is not a big deal here. Do you know why, Sydney? It's a symmetric matrix. So just for the purposes of illustration, I am going to change that to 0.8. And then I'm going to change it right back. So, oh, n row. So, row hat, vector, 0.64, negative 0.6, which is P2, I have 1.64, 0.64, 0.8. But if you set it The default value is false. We need to set it to true. It's going to get the same matrix. So let's change out to 6. One more time.
What's the reason that the matrix has the 0.08?
Oh, I'm going to change it. I just want to demonstrate whether to use true or false with 5. That's all. Our matrix is symmetric. We won't see a difference. So I'm getting 1, 0.4, 0.6, 0.8. So it takes the first 2 values, puts it in the first row, next 2 values, second row, but if you don't specify, the default value is false, it will start filling this way. Firstly, 1, 0.4, 0.6, 0.8. So you've got to be careful when you define it in R. For this example, though, it doesn't matter because we have a symmetric matrix. 6,4 and then 0.64, 1. My context students, you can enlighten me how to invert a matrix and find a solution. Solve, okay. If I don't specify row dot hat, and I simply did solve P 2, it is going to give me the inverse of the matrix. But I want to solve and get an answer. So P dot hat, solve the matrix, and the vector on the left hand side earlier, so row dot hat. Good. Which is more accurate, this one or the one given by the calculator? Well, as a general question, which is more accurate? R or calculator? Definitely R. More precision. You just don't see it, but in the background, it has more floating point position or higher floating point position. Okay. Let's see. Did it come from a stationary series? I made this up. So my fitted model fitted AR2 model. XT equals 1.266 xt minus 1 minus 0.6 x of t minus 2. Do we remember the function that we used to simulate the series? No. Oh, you missed it. Got to give the sample size. So n was 128. Got to specify the model coefficients, 1.26, common, negative 0.96. Good. I'm changing or creating variables so that you can play around at home. So let's see. Fingers crossed. Type equals L. Four. Good. So it does correspond to an AR series, and that is the series. If I simulate, am I going to, by simulate, I mean if I run it one more time, am I going to get the same series? No. I didn't set a seed. So something different. Interesting. If you look at this pattern, you might say, well, what kind of series is this? You don't see something like that in business, but you definitely see it in signal processing. Something like that, voice recognition, probably corresponds to a consonant, a diphthong, or a vowel. I don't know which one's which, but when I speak, the word speak, the vowel part might look like that picture. So you can recognize a person's pitch, voice, convert to text, all kinds of stuff. Okay, just an extra bit of information. If I did the ACF, thanks. Two. And I'll also do PACF, thanks. Color 4. ACF starts at row 0, so I have 1. Row 1 is 0.5 something, but that is nowhere close to 1.26. Agreed? So, not going to work. The only time ACF is going to work is when you have an AR, one more. PACF, you look at the plots, and there are 2 lines or 2 vertical lines that go outside the dot. Yes, that tells me that I am looking at an AR2 series. Good. So by observing a PACF course, I can determine the order of the AR series. Once I determine the order, I can use Yule-Walker method to fit the model. Good. So where would I have started in practice? In practice, that's where we start, because that is our observed series. If someone gives me that, I'm going to look at it and say, I have to fit an AR model, probably, maybe MA, I don't know. But let's ask the question, is it stationary? To my eyes, it looks stationary. Right, okay. So perhaps an AR model would work. So the next step would be to go for a PACF, not an ACF. ACF works only for an AR model. So that would be my next step. I look at 2 significant peak values. That tells me the model I need to fit is AR2. Now that I've identified that I have to use an AR2 model, I go back to the ACF. Any thoughts why?
Check for error. Check for
No. So I have a series. First, I asked the question, is it stationary? Looks stationary to me. So I move on, get the PACF. It is giving me the order. It tells me an AR2 model is going to work for that particular series. Now I'm getting the ACF.
To officially check the stationary. Like when you look at the ACF, you're looking to see the stationary, like check messenger.
True, but in the context of what we did today,
So for with coefficients.
right, there is no way that I'm going to fit the model without the autocorrelation. Agreed? So I will do the ACF. Those are not values. You've got to ignore the first one, that is row 0. It is always 1. It tells me row 1 is 0.618. Look up there. 0.64. Row 2 is negative 0.144. Negative 0.16. So the one that I made up arbitrarily makes perfect sense. Good. And you may ask, well, it's a bit off. Well, it is off because the length of the series is 128. After I post the script, play around with this, you know, we have that saying, the bigger the sample size, the better everything is, right, in statistics. If you increase the sample size, you would see that these values approach those. It'll get closer and closer. One last question. Here I have 1.26 and negative 0.96. Look at that and say, well, 1.26 is outside the unit circle, but negative 0.96 is inside the unit circle. And we already established that the series is stationary. Are we conjugating? Or are we misinterpreting something? It's a common mistake that people do. Or maybe. We don't establish stationarity by looking at phi1 and phi2. Our condition inside the unit circle, outside the unit circle, don't directly correlate to phi1 and phi2. For an AR2 model, we will get a characteristic equation which would have phi1 and phi2, but that characteristic equation is a quadratic function. So you find the roots of that quadratic function must lie outside the unit circle. Good. I want you to give it a try at home. I will set the stage here, but you can play with it after I post it. So you've got ACF, PACF, everything, and use the true model, 1.26 for phi1, negative 0.96 for phi2. Write the characteristic equation, find the roots of that characteristic equation, and see if they lie outside the unit circle. Good. Okay.